So, good morning, everyone, and welcome to this lecture. We are going to start with electronics, this branch of physics inside modern physics, known as electronics. And we are going to deal with semiconductors in this particular uh, topic. Now, this branch is known as, this topic is known as electronics. And when I say electronics, it's derived from the word electron plus dynamics, which means that we are going to study the behavior of an electron under different conditions of externally applied electric field. Now, this field, electronics, deals with electronic devices. It deals with electronic devices and their uses. Uh, in this field, in this part, we are going to study electron devices and their utilization. An electronic device, a device where conduction takes place by the movement of electron. Now, some of the devices that we are going to study here will be amplifiers, rectifiers, oscillators, and so on. So these are the snippets of what we are going to do in this particular chapter. We are starting with electronics. You don't have to write all this. This is just for your knowledge that I have given you this. This is not required for you to note down. Now, let us move on to things which are more useful. Since in electronics we are going to study these electronic devices will be made from certain type of substance or material. Now, if we can divide the substances that we see into three categories, and you must be aware of these three categories. The first category is known as metals, then you have insulators, and in between metals and insulators we have got something which is known as semiconductors. I hope we know all this. Metals, they are good conductors and they have very low resistivity. Insulators have very high resistivity. Semiconductors have resistivity or conductivity which lies between metals or conductors and insulators. Do we know this, everyone? Yes or no?
Yes, sir.
Do you need to note it down?
No, sir.
Okay, then this is a table that I am going to show you, which now in this particular chapter what we are going to deal with is not metals or insulators, conductors or insulators. What we are going to deal with is semiconductors. Now, to understand what are semiconductors or what are metals and insulators. There is a very important concept that you must remember, and that concept is the concept of energy bands. Have you heard the concept of energy band? Have you heard the concept of energy band?
Uh, no, sir.
Never heard the term energy band?
Uh, we heard it, but don't remember exactly.
Now, if I have an isolated atom, then we have if I have an isolated if I have an isolated atom, then we will have different discrete permissible energy levels. We have seen this in the structure of atom, yes or no? P shell, K shell, L shell, M shell, and N shell, and so on. Do we remember this?
Yes, sir.
If we have an isolated atom, we will have distinct or discrete levels of energy. Do we understand this? Whether it is n is equal to 1 or n is equal to 2 or n is equal to 3 and so on. But when it becomes a solid, when there are a lot of atoms present, they are interacting with each other. Now, because of this interaction, instead of having isolated or discrete bands like this, n is equal to 1, n is equal to 2, instead of having one specific value, they have a range of values. They don't have one specific value, they have a range of value. This range of value is known as the energy band. So they will have a range of value for the first band, they will have a range of value for the second band, third band, and so on. Now, the last shell, now we'll not call it shell, we'll call it band. The last band is known as VB. VB means valence band. Do we understand this? And then every shell above it will be known as CB, which is known as conduction band. So if you have an isolated atom, you will have discrete single value energy shells. But when you think about in a solid, they are interacting with each other. So instead of having single value energies, they have energy in a range. This range is known as energy band. Do we understand this?
Yes, sir.
I'll give you 2 minutes to note it down. So as you can see, this diagram tells us the same thing. When you have a single atom, the energy of the shell is one discrete value. If you bring here, it is taken two sodium atoms, and when two sodium atoms are brought close to each other, this is how the energy levels look like. One has, instead of having one discrete value, it has two values. 2s also has two values. If you bring five atoms together, these are the values. So you can imagine If there are even a 1 mole of there are even 1 mole of atoms, which is very small, this will not be discrete value. This would be more like a value between two extreme values, or the energy level of 2s or 1s or any of the shells will be having an energy band instead of a discrete level. Do we understand this?
Yes, sir.
Everyone understands this? Now, whenever we talk about the energy bands, we must understand what are the type of energy band. The first type of energy band is known as the valence band. That is what we are concerned about. This energy band is formed by a series of energy levels containing valence electrons, large shell. Do we remember valence electron?
Yes, sir.
At 0 Kelvin, the electron fill the energy levels in the valence band starting from the lowest one. Remember this. Starting from the lowest one, they fill. Facts, this band is always filled with electrons. This is the band of maximum energy. Electrons are not capable of gaining energy. No flow of current. If electrons are present in the valence band, they are not free electrons. They do not consist current. The highest energy level which can be occupied by an electron in the valence band is known as Fermi level. I have seen questions based on Fermi level, so please remember this. Now, if one band is known as valence band, what will be the other band known as? The other band will be known as the conduction band. The next higher energy band is known as the conduction band. It is always empty, it is partly filled. In this band, electrons can gain energy from external fields. These electrons are known as free electrons, and current flows because of these electrons. Now, there is always a energy difference between the valence band and the conduction band. This energy level difference is known as forbidden energy gap, or delta Eg, which is the energy difference between the valence band and the conduction band. I'll give you 2 minutes to note this down. All these are simple facts. Remember, most of the questions that are coming in this modern physics are sometimes assertion and reasoning. You need to know all these points, because single point can make you miss or hit that question. So here we come with a diagrammatic description of the same thing. The energy difference between the valence band ka minimum value and sorry, conduction band ka minimum value, and see, this is conduction band minimum, and this is valence band maximum. Do we understand this?
Yes, sir.
The difference in these energy levels, the difference between these two bands, is known as the forbidden energy gap. In the forbidden energy gap, there are no free electrons, they cannot exist. Now, this forbidden energy gap depends on the nature of substance. If the width is more, then the valence electrons are more strongly attached with the nucleus. Width of this is expressed in electron volts. We have just seen electron volts. As temperature increases, sometimes the energy gap may decrease very slightly. And now you can see in different types of bodies what is the width. In a conductor, you can see this valence band and conduction band are overlapping. That is why a lot of electrons are present in the conduction band, and therefore they are good conductors. Do we understand this?
Yes, sir.
In case of semiconductor, you can see between valence band and conduction band there is a small energy gap. 1 electron volt is considered to be a small energy gap, and therefore Their conductivity lies between conductors and insulators. When you see insulators between valence and conduction band, the energy gap is more than 3 electron volts, and that is why they are insulators. I'll give you a minute to note this down. So again, we can note down the same things in terms of points. In a conductor, there is no energy gap. The conduction and the valence band are overlapping, so the forbidden energy gap is zero. In insulator, it is greater than 3 mega electron volt. In semiconductor, it is very, very small. Do we understand this?
Yes, sir.
Okay. Now, here comes this table which encompasses everything that you need to know about this properties of conductors, insulators, and semiconductors. Electrical conductivity of conductors is very high, insulators it is very less, semiconductors will always lie in between the two. Resistivity, you don't have to remember these values, you just have to remember these band structure. How are these band structure? What is the energy gap? What are the current carriers? In conductors, the current carriers are free electrons. Here we have no current carrier. Here we have free electrons and holes. What are these holes? We will see this. What is the condition of valence band and conduction band and ordinary temperature? Valence band and conduction band are completely filled because there is an overlapping. Valence band is completely filled. Conduction band is completely unfilled. Valence band is somewhat empty. Conduction band is somewhat filled. Question based on this can very well come in your exam. I'll give you a minute to note this down. Then we come to this fact, what happens when temperature is increased. When temperature is increased, the temperature coefficient of resistance is positive for a conductor. Therefore, the conductivity decreases and resistance increases. But for semiconductor, it is reverse, and that is a very important thing that you must remember about a semiconductor. With increase, with increase, with increase, with increase in temperature, the resistivity decreases and conductivity increases. That is what you must remember. I'll give you 2 minutes to note it down. So now we can move ahead, and in very short and very quickly, you may write the properties of semiconductors. The properties of semiconductors. The properties of semiconductor. Remember, most of the questions that you are going to get from this chapter will be more theoretical, and therefore you will have to remember a lot of things about semiconductor. The first thing is negative temperature coefficient. They are crystalline structure with covalent bonded. They have phase center cubic. Conduction
Sir,
properties may change by adding small impurities. Yes, they always lie in the fourth group. Their forbidden energy level is between 0.1 to 3 electron volts. The charge carriers are electrons and holes. And basically, whenever we are talking about semiconductors, we are talking about two particular metals, germanium and silicon. These are the two semiconductors that we would be discussing. Now, remember what is the effect of temperature on the semiconductors at 0 Kelvin. There is no electron which is present in the conduction band, and therefore it acts like a perfect insulator. At any temperature which is above 0 Kelvin, it will behave as a semiconductor. Its conductivity will lie somewhere between insulators and conductors. I'll give you a minute to note this down.
sir,
Well, then we move ahead with these important points. The number of electrons reaching from valence band to conduction band. No one is going to ask you this, but still, it is given in this form. Just remember it is how it is proportional. T is the absolute temperature. Eg is the forbidden energy gap. K is the Boltzmann constant, and A is a constant. At room temperature, in silicon, out of 10 raised to the power 12 silicon atom, only one electron goes. So you can see at room temperature, pure silicon is not such a very good conductor. At germanium, for every 10 raised to the power 9 germanium atoms, only one electron goes from valence to the conduction band. So the number is very less. That is what you need to remember. Now we come to a very important concept, and that concept is the concept of holes. The concept of holes in a semiconductor. What is this concept of hole? At absolute zero, we have seen that the conduction band of semiconductor is completely empty, and this conductor actually behaves as an insulator. Now, what happens when the temperature is increased? The valence electrons acquire some thermal energy to jump to the conduction band. So, electrons move from valence band to the conduction band. When they jump to conduction band, they leave a deficiency of electron in the valence band. So, when an electron is jumping from conduction band, it is leaving a vacancy in the valence band. Do we understand this? Now, this vacancy in the valence band, even though it does not have any charge, it will behave as a virtual positive charge, and this virtual positive charge is now known as a hole. This virtual positive charge, which is created by the vacancy of an electron jumping from conduction band from valence band to conduction band. You can see here they are showing these gaps here. They are showing these gaps here. What are these gaps? These gaps are nothing but electrons jumping from valence band into conduction band that creates a deficiency of electrons. This deficiency of electrons, which is created in the valence band, is known as a hole. So what is a hole? It is a missing electron. It acts as a positive charge. Its effective mass is more than that of an electron. Its mobility is less than that of electron. These are the properties that you must remember. Hole acts as a virtual charge. There is no physical charge. Free electron is moving in the conduction band. Hole is moving in the valence band. You do not need to draw the diagram. The diagram is just to illustrate that because of some electrons jumping from the valence band into the conduction band, vacancy is created in the valence band. This vacancy is known as hole, and it behaves as a positive charge. It behaves as a virtual charge. The charge of a hole is same as the charge of an electron in the positive way, but the mass is more. I'll give you a minute to note this down. Let me start it. Okay, so whenever you have this intrinsic semiconductors, you will have a current which is present due to the movement of electrons. You will have a current that will be due to the motion of electrons. Electrons will be moving in the conduction band. Holes will be moving in the valence band. They will be moving in the opposite direction, but the current due to them will be in the same direction. The one current, which is because of the flow of holes, is known as the hole current. The other current is known as the electron current. The net current will be the sum of the two currents. I hope this point is very clear. You may just note it down. Once you have noted it down, please raise your hand so that we can move further ahead. Let us move ahead and see the same thing in terms of the two diagrams. Whenever you have an intrinsic semiconductor, then you apply potential difference. What you need to remember is that the electrons are moving in the conduction band, whereas the holes are moving in the valence band. The direction of motion of these two are different, but the current is in the same direction. The total current will be the current due to the electrons plus current due to the holes. Current is NAEVD, where N is the hole density or the electron density. This is the This is one equation that you must remember. What is the current in an intrinsic semiconductors? Once you have the current, from this current you can find out the conductivity of this intrinsic semiconductors, and it is a very important result. The conductivity of this intrinsic semiconductors is given by E into Ne into mu E plus Nh into mu H, where Ne and Nh are the densities or the number of electron and holes respectively. Mu E and mu H. Remember, many questions have come on this mu E and mu H. Mu E and mu H are the mobility of the electrons and holes. Remember, the mobility of an electron is always greater than a hole. I have told you this. These points are coming in the exam these days, and therefore I'm marking them. They might be coming. They might be coming as assertion reasoning questions also, my dear friends. So remember this. Every point that you are writing in this is a potential question. At room temperature, the conductivity of germanium is more than the conductivity of silicon. I shall give you 2 minutes to note this down. Remember the other 2 points. Conductivity of a semiconductor will always increase with temperature because more electrons can jump into the conduction band, more holes are created, current increases. Remember, this is a very important result. In a doped semiconductor, now what is a doped semiconductor? We are just going to see it after this slide. In a doped semiconductor is a conductor which has some added impurity. That is the second type of semiconductor. The electron density and the hole densities are not equal, but it can be established that Ne into Nh, density of electron multiplied by density of hole, is Ni square, where Ne and Nh are the number density of electron and hole, and Ni is the original number density of intrinsic carriers in a pure semiconductors. It's a very important result, and I give you 2 minutes to note this down. So we now come to The next heading, which is extrinsic semiconductors. You don't have to write everything down, you just have to understand and maybe note down the important point. The conductivity of an intrinsic semiconductor depends on its temperature, and at room temperature it is very, very low. It is practically useless. A semiconductor, a pure semiconductor, a intrinsic semiconductor at room temperature is practically useless because the conductivity is very low. But we can improve this conductivity by adding some other elements into it. Those elements, those materials which are added are known as impurity, and the semiconductors in which those materials are added are known as extrinsic semiconductor or impurity semiconductors. These materials which are added are known as dopants. So you take a pure semiconductor, silicon or germanium, you add other stuff, and now it becomes an impure semiconductor. Such semiconductors known as extrinsic semiconductors. There are two types of impurities that you can add: pentavalent, like arsenic, antimony, or phosphorus, 5 electrons in the outer shell, or trivalent, like indium, borium, aluminium, etc. In short, what you have to note down is extrinsic semiconductor is a semiconductor in which impurities are added to improve the conductivity. I'll give you a minute to note this down. So now you have these extrinsic semiconductors, a quick snapshot. You have the original intrinsic semiconductors, you add this gentleman impurity, and you get this new gentleman extrinsic semiconductors. It is also known as impure. The impurity is known as, the process of adding impurity is known as doping. The impurity is also known as dopant. Impurities are of two types. The first one is pentavalent, which has 5 valence electrons in the outermost shell. They are also known as donor impurities. These impurities are also called donor impurities because they have an extra electron which can be given. On the other hand, we have trivalent, like aluminum, boron. These impurities are known as acceptor impurities because they have one less electron. They are from the third group. They have got one less electron. They can accept electrons. They are known as acceptor impurities. The number of atoms of impurities generally 1 is to 1 in 10 raised to the power 8 atoms. Now the number of electrons will not be, the density of electrons will not be equal to the density of holes. Very important point, a question came on this. In this, the Fermi level will shift towards valence or conduction bond depending on how it is doped. Their conductivity is very high and they can be practically used. Very important results for this extrinsic semiconductors that you must remember and you must not forget these points that are being made. I'll give you a minute. I'm looking for something. Okay, just note this down. I'll give it in the next slide. Now remember, all these things, majority of this chapter is about theory, and if you can remember points, you are going to do very good in this particular chapter. Now, since we have seen that there are two types of impurities and therefore there are two types of extrinsic semiconductors, the N type and the P type. In the N type semiconductors, what we are doing, we have a pentavalent impurity which has 5 electrons. It has 5 electrons like phosphorus or arsenic. Out of this 5, 4 electrons will combine with silicon or germanium crystal, but 1 electron, as you can see, this green one, remains free, and therefore this is known as a donor impurity. These type of semiconductors, the number of electrons is very high compared to the number of holes. Therefore, the electron current is higher compared to the hole current. The majority charge carriers, current carriers are electrons, and minority carriers are hole. Therefore, and the number of electrons are very high. Therefore, you can say the conductivity is Ne into mu E into E. The donor energy level is just below the conduction band. Very important result. This has come in the exam. The donor energy level is towards the conduction band. Therefore, the Fermi level will shift closer to the conduction band. Electron and hole concentration, I already told you, Ne into Nh will be always equal to Ni square. Do we understand this? Can I have raised hands from everyone that we understand this? This chapter, my dear friends. 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 It's all about. It's all about. It's all about remembering the points. Let me put the rest of the points in the same table so that I don't have to do it. The impurity atom is called the donor, which are elements of 5. We also know this. The net charge on the n-type crystal is 0. Just don't see or understand that since electrons are more, the charge is more. No. When we talk about this crystal as a whole, it is electrically neutral. It's only the concentration of holes is less than the concentration of the electrons. Immobile charge is the positive charge. It does not move. The current is almost zero because of the hole current. I'll give you 2 minutes to note this down. And the next type of semiconductor is, my dear friends, a P type semiconductor. You have impurity of third group. One electron is less than the fourth group. So you have a vacancy of a whole. The accept energy level should be near to the valence band because holes are to be created. Number of holes becomes equal to the number of acceptor. They are not an acceptor because they accept electrons, and it is very high compared to the number of holes. Remember, net charge is 0, immobile charge is negative charge, majority charge carrier now become hole, and minority carrier becomes electron. They are so less that the electron current is very small. So I can write the conductivity as mu h into nh into E. They are also electrically neutral. Impurity is called acceptor. The acceptor level is for P type, it is nearer to the valence band. I hope everyone understands this. I'll give you a minute to note this down. Then we can move ahead, and then this one small table we can summarize the difference between intrinsic and extrinsic. Remember, this chapter is all about knowledge. Intrinsic semiconductors, pure concentration of electrons or holes are equal. Electrical conductivity is very low. Conductivity cannot be controlled. Its conductivity increases exponentially with temperature. But when we talk about the extrinsic semiconductors, it prepared by adding a small quantity of impurities. The concentrations are unequal in n-type. Electrons are more in p-type. Holes are more. The electrical conductivity is significantly high. The conductivity can be controlled. The conductivity also increases but not exponentially. For an intrinsic semiconductor, it increases exponentially. I'll give you 1 minute, 2 minutes to note them down fatafat. Then we come to this astonishing table, n-type and p-type summarized very carefully. In the n-type, we have a pentavalent impurity, the donor impurity, majority charge carriers are electrons, minority are hole. Number of that the number density of electrons is very high compared to hole. Electron current is more than hole current. The number of electrons is approximately equal to the Donor, the density of donor, conductivity, only mu E and Ne will come. These are electrically neutral. The impurity is known as donor. Everything is known as acceptor. I know this. I know that you know this. Put it in the table. Last but not the least, you must remember that for an N-type, the donor energy level is nearer to the conduction band. For P-type, the donor energy level, the acceptor energy level is nearer to the valence band. These are very, 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 very important results that you must remember. Give you a minute to note this down. And let me give you question based on this. Let me see. Here are the questions. Okay. I hope everyone has noted this down. This is the first question that is coming up. A germanium specimen is doped with aluminium. The concentration of the acceptor atoms is this. Given that the intrinsic concentration of electron hole pairs is this, what is the concentration of electrons in the specimen? This is how questions are framed in a JEE. I hope, I hope, I hope, hope that you are able to solve this. So how must you do this? You must remember the formula Ni squared is equal to Ne into NH. Ni is the intrinsic concentration, my dear friends. That is given as 10 raised to the power of 19. So 10 raised to the power of 19 squared should be equal to 10 raised to the power 21 multiplied by NH. And when you solve this, my dear friends, you must end up with the option A, and that is the answer 10 raised to the power 17 per meter cube. I hope you understand this. The next one in line is this one. Remember, the questions from this chapter are going to be pretty damn simple. You just need to take a deep breath, close your eyes, look at the question, remember what has been told to you, and trust me, not even a single question can come out of what I am telling you. Not even a single question can come from the out of the question that I have done in the class. The only thing that you have to remember is to remember that we have done this. The only thing you need to forget is to forget the habit of forgetting things. And I hope that this happens before it's too late. This is the next question. A silicon specimen is made into a p-type semiconductor by doping on an average 1 indium atom per 5 into 10 raised to the power 7 silicon atoms. If the number density of atoms in the silicon sample is this one, then what is the number of the acceptor atoms? Whee! You have 2 minutes to give me the answer. So, how do we find out the value for this one? You can see that on an average, 1 indium atom is added for 10 raised to the power 7 silicon atoms. So for 5 into 10 raised to the power 28 atoms per meter cube, the number of indium would be 5 into 10 raised to the power 28 divided by 5 into 10 raised to the power 7. So that will come as 10 raised to the power 21 atoms per meter cube. You have to just convert it into centimeter cubes. And I hope you know how to convert it. The answer would be option C, my dear friends. Option C, my dear friends. Option C, my dear friends. And that is the answer for this particular one. I hope everyone understands what we are doing here. Let me present one more question for you, and this is this one. Pure silicon at 300 Kelvin has equal electron and hole concentration of this. Doping by indium increases NH to this one. Calculate Ne in the doped silicon. You have 2 minutes to give me the answer. I hope you have got the answer for this one, my dear friends. You must remember Ni square will be equal to Ne, the concentration of the electrons, multiplied by the concentration of the holes. The concentration of the holes is given here. You can easily find out the concentration of electrons. The concentration of electrons with intrinsic concentration square divided by the concentration of the holes. So intrinsic concentration. Oops, what has happened? Intrinsic concentration square divided by NH. That is what we have to find out. So basically that gives us 1.5 into 10 raised to the power 16 squared divided by 3 into 10 raised to the power 22. That is going to give me an answer which is 7.5 into 10 raised to the power 9 per meter cube, and that is the answer, my dear friends, that I was looking at. I'll give you a minute to note this down. Till the time I move on to the next question, remember one of these questions, even with the same values, is if it comes, it will come from this segment. It will be one of these questions that we are doing right now. Here comes the next question. Now again I am doping silicon at the same temperature. Electron and hole concentration is same. Now doping by indium increases it to 4.5 into 10 to the power 22 per meter cube. What is Ne? Wait for a minute to for you to give you the chance to give me the answer. I hope you would have got the answer for this one. Again, Ni square will be equal to Ne into Nh. From there, you should be able to find out the value of Nh. Nh will be 1.5 into 10 raised to the power of 16 whole square divided by 4.5 into 10 raised to the power 22, and the answer that I have with me is 5 into 10 raised to the power of 9 per meter cube. I hope you have got the same answer for this one. That will give you confidence. Remember, one of these questions is going to come in your exam the next attempt. Having said that, let us move on to other questions. Remember, we are targeting to clear exams. This is the next question, a very simple one. The majority charge carrier in p-type semiconductors are. I hope everyone is there. Can I have the answer for this one? Majority charge carrier in p-type semiconductors are. And the answer is option C. They are definitely holes. Remember these simple things. One of these questions is going to end up in your paper, and you must be well versed with solving it and getting your answers. The next one, when a semiconductor is heated, what happens to its resistance? When a semiconductor is heated, what happens to its resistance? And the answer to this one is pretty simple. The temperature coefficient is negative. As the temperature goes up, more electrons can move from the from the valence band to the conduction band. The conductivity increases, resistivity as such decreases. Remember these important facts. That takes us to this question, the next one in line, and I'll give you 2 minutes to think about it and give me the answer. Which of the following energy band represents a n-type semiconductor? And the answer is definitely option 2. The impurity level, the acceptor level is near the conduction band. Simple things. If you remember, my dear friends, I'm sure any question that comes from this part, and I will show it to you, the questions that have come, and you might see any question that we have done. We'll see that similar question was there in your exam, maybe this year or the last year. Which of the following energy bands correspond to that of a semiconductor? The answer is definitely EG. The forbidden band is almost equal to KT. It is very less. Remember, that is why it is known as a semiconductor. Otherwise, it will not be known as a semiconductor. I hope everyone is getting what type of questions we are supposed to face. Again, let us see. If I frame the question in this way, can you solve this? A p-type semiconductor has acceptor level of 57, small m eV. Small m, remember, stands for milli electron volt. Capital M stands for mega, small m stands for milli. 57 milli electron volt above the valence band, the maximum wavelength of light required to create a hole is. So, how are we supposed to solve this? Energy is hc by lambda, my dear friends. The energy required is hc by lambda. We always know that lambda is hc by E. We have done it 1500 times, maybe more than that in the previous 10-15 days. Anyways, you can write it approximately equal to 12,400 mega electron volts divided by Armstrong unit, the wavelength in Armstrong unit. So lambda will simply be equal to 12,400 divided by 57 into 10 raised to the power minus 3. Instead of taking it as 57, you can take it as 60, and you will end up with an answer, and the answer will be 217100 Armstrong units. 2700 Armstrong units. I hope you understand this, and I sincerely hope that You would remember this till the time your exams are over. I'll give you a minute to note this down. Meanwhile, I will just move on to the next question. And the next question looks like this. Everyone has noted this down? Well done. You're good at noting things. And this is the next one. The energy of a photon of sodium light is 589 nanometer, equals the band gap of a semiconductor material. Find the energy required to create an electron hole pair. Well done. So I have an answer now. You can straight away use lambda is 12,400 divided by lambda. What I am doing. The energy E is hc by lambda. So you can just write it as 12,400 divided by lambda in Armstrong unit, and the energy will be in electron volts. This will be 12,400 divided by 589. You don't have to divide it by 589. You can divide it by 600 and you will end up with 2.1 electron volts. So 2.1 electron volts is the forbidden energy gap, and that would be equal to the energy which is required to create an electron hole pair. I hope everyone understands this. Just a table I am going to show which tells us the comparison between intrinsic p-type and n-type semiconductors. Remember, in intrinsic, Ne is equal to Nh. Here holes are more, here electrons are more. For this J, remember, is current density. This J here is current density. In case of intrinsic semiconductors, current density is because of hole and electrons together. Here it is approximately equal to hole because electrons are very less. Here it is approximately equal to electron density because the other things are zero. If someone talks about sigma, the sigma in this case will be, remember, sigma, whenever we are talking about sigma, we are talking about sigma, we are talking about the conductivity, and the conductivity in this case will be equal to E multiplied by N because the concentration is same. This will be mu H, mobility of plus mu E. Here this conductivity will be equal to E into NH into mu of H. Here the conductivity will be E into N of E multiplied by mu of E. I hope you understand this. Remember these formulae. One of these questions is going to land up in your exam. So this is the question framed on this. What will be the conductance of pure silicon crystal at 300 Kelvin? The electron pair per centimeter cube is something something. Mu H is something something. Mu E should not be mu P. Mu E is something something. So how are we supposed to solve this question? Conductivity will be given by N into E into mu H plus mu of electron And how do we get this? I think this is given in the reverse sense. This should be mu of hole, and this should be mu of electron, because mu of electron should be more than the mu of hole. Anyways, you just need to put the value. Sigma will be equal to n. The concentration is 1.072 into 10 raised to the power of 10 multiplied by 1.6 into 10 raised to the power of minus 19 multiplied by 1350 plus 450, and the answer that I have is 3.14 into 10 raised to the power minus 6 mole per centimeter with the correct unit. Just a question of multiplying and dividing. If you know the formula, the only time it would take would be in multiplication and addition. That brings us to an end of today's class. In today's class, we have had a very good start to our quest in semiconductors. We have seen what is semiconductors. We have seen pure silicon, pure germanium, intrinsic semiconductors. The number of electrons and holes are equal. At 0 Kelvin, there is no conduction electron. When temperature rises, electron jump. Then we have extrinsic semiconductors, N-type, acceptor, P-type, donor, and we will continue with this the next class. In the next class, we will see PN junction and we will see the various devices. So we'll try to wrap it up in the next class if possible. Take care. God bless all of you. If you have any doubts, please come up. Bye bye.